Okay, now let's see what kind of a flow vortices create around an airfoil. To begin with the vortices, I want to keep my covers here, but take away this part off. So I want to take that off. Okay, so this is also not part of that. So to be able to do the vortices, let us create a mesh grid. Okay, so this is my mesh grid. Okay. I want to have my x velocities and y velocities defined along the mesh grid in this way. I don't want to plot it yet. Now, okay, so here is a mesh grid. And then to begin with, I want to start with 3 simple vortices like that. Now, these are the y coordinates, and these are the x coordinates. Sorry. So these are the x coordinates, that's the y coordinates, and these are the vortex intensities, all equal to 1. Okay, so the velocity, I defined the velocities up there already. So this is my free flow, so not necessary to define it again there. So remember from the previous videos, this is how we calculate the final flow velocity, ux and uy, using the vortices in a zipped format. So if you need, do a review of how we superpose vortices and then do the stream plot due to these vortices. Okay, so to begin, before running the program, let me go over the program to make you understand this better. After my function definitions, I get a foil, x and y coordinates, the foil panel centers, panel normals. I plot the panel normals here, and then I define a mesh grid and a free flow. So I have a free flow here and 3 vortices with these coordinates and these intensities. So I go over the vortices and then update the flow field and then stream plot it. So let us do this. Okay, here is the airfoil and my 3 vortices, all in the counterclockwise directions over there. So I can change. So if I want to move this vortex exactly on the origin, you will see that this vortex will be at the origin there. Okay, so it's very near to the leading edge. And then I can also push this towards there as well. So that can be 1, and I think 0 should suffice at this point. Okay, and then how about we put this somewhere here. There is no point of moving them around. I'm doing this to familiarize you with how I control this. So okay, it's almost at the center already. And how about we make this 2 times larger compared to the other vortices and in the clockwise direction. Okay, it's good. Now you might be asking, where is the free flow here? I should have the free flow. As you see, it's here. I define it there. But because the free flow, our vortices are quite large, so the free flow doesn't really show its face there. So if I make the free flow 10 times larger, we will begin to see the free flow, because now the vortices will be, their magnitudes will be less compared to the free flow. Okay, now you will see it nicely. So there is a free flow going this way, and these three vortices are actually disturbing the flow. I can make it even more pronounced by doing 20 here. Okay, see, the free flow is now less disturbed by the smaller vortices, but still this 2 times larger vortice is making itself visible. And if you make the free flow larger with respect to the air, to the vortices, you will begin to see a slightly disturbed free flow. Okay, I think we are beginning to understand what is happening here. I want to return back to 10. This is good enough for my purposes now. Okay, so I have three vortices and the free flow, and this is the net flow due to that. Now, the next question is how to do the projections of this flow, how to do the projection vectors on the panel normals. That is my main question. Next, I want to discuss that. I would like to do the projections now at the panel centers. So I don't use a mesh grid for that. Instead of the mesh grid, I use for x and y coordinates the x center and y centers. Okay. So these are the panel centers. Instead of a mesh grid, I have my, if you want to think of the mesh grid, I have my grid now at the x center and y center points. This is an irregular grid that I introduced in the very beginning of these videos. So this is an irregular set of coordinates, even so they are not even a grid in this the right sense of the word. So at the panel centers, I define a free flow in the x direction. Okay, that's good. Now next, I want to, let's have this, let's keep using the same vortices that we had in the previous program. Okay, and this part actually calculates ux and uy components of the net flow. Good. So when I have my ux and uy, so I start with a free flow, but the vortices change that flows. Then I have new ux and uy available here. I can simply use a curve plot projection that we did for the free flow, exactly the same. So let me plug it here. So let's see. Projection of ux, uy flow vector along the normal nx and y vector. So I don't define this anymore here, but the projection is now the normal vector times the ux, normal plus normal vector, normal vectors y component times the y component of the velocity. So I add this to do the projection and do the curve plot here in the exactly the same way I did before. Let's make this less transparent, more transparent, and I need a larger scale, I think, to be able to do this. Okay, let's run this and then I describe what we see on the picture. So I see the normal vectors, and also I see the projection vectors. The projection of the flow vector along this normal vector. For example, for this one, it's in the opposite direction. For that one, I have for the one that shows the uh, uh, lower panel normal. So I have a large normal flow in this direction. The flow is much more irregular for this case, as we just see using the stream plots. I want to make this scale even larger to make them smaller. So what do we see on this picture? Let me try to explain once more. So I have a free flow, and on top of that, here on the program I want to explain, I have a free flow and three vortices, and then this creates a flow field. The flow field components are ux and uy. Now, once I have my ux and uys, I can do the projection vectors along the normals, and that's a simple projection that we described before. So that is the scalar product of the normal vectors and the flow velocity vectors, the components. Once I have the projection magnitude, I can multiply the normal vectors with that. So this diagram basically shows the projection velocity due to the vortice and the free flow along the surface normals. Okay, now I have the projection vectors due to my velocity field. Let us visualize the velocity field on top of the projection vectors. In order to do that, I have to calculate the velocities for each uh, grid point to be able to do the global stream plot. Therefore, I need this part again. So let us take this. Okay, I have my grid is defined. I want to do this underscore so that it doesn't confuse with the x and y of the foil coordinates, since I don't use this x and y again. Okay, I have my mesh grid. Then I need my free flow velocity here. Okay, here's my free flow velocities. I can also keep them there as well. But after, when I execute these lines after this too, the shapes will be different when I do it here. Okay, so I have my velocity, free flow velocities initialized. There is my vortices, so let's keep them there, but do the calculation for different mesh grid points here. Okay, once I have my ux and uy calculated for the mesh grid points, I can do the stream plot. And the stream plot will, okay, ux and uy. So on this graph, I see my panel normals and the flow velocities component along the panel normals due to these three vortices and the free flow superposed. Now at this point, the question is that the flow, let us follow the flow here. So the flow, as you see, goes through the airfoil, which is not acceptable. In real life, flow should not go through the airfoil. Can you see that the flow actually goes through the airfoil? So these are the components here, and this is the flow field. Yes, the flow field does not curl around the airfoil, but it goes through the airfoil, and the presence of these projections are actually showing me that there is a flow into the airfoil, which should not be. So now I am ready to ask the question, how can I find the values, how can I find the right vortices so that the flow curls around the airfoil? Now I have a better insight to that problem. The flow will curl, when the flow curls around the foil, there will be zero projection vectors. So the projection vectors will be all zero if and when the flow nicely curves around the airfoil. How can I make the projection zero to make the flow curl around the airfoil? What are the values and the positions of the vortices that will make the flow nicely curl around? Now, this is not an easy question. Here is where I define my free flow and my vortices. So I use 3 vortices, and they are completely random vortices, and therefore I get random projections. But I want to find the vortices that will give me exactly 0 projections. Let us play with that a little bit. How about we do this one minus as well? Of course, we can't do it this way, but I want to show you the flow and the projections change. See, the flow and the projections change as I change the vortices and their locations. At this point, I suggest instead of 3 vortices, we use a relatively large number of vortices. How about we place a vortex at each of the airfoil points, not the panel points, but the airfoil points. So I want to put a vortex at each of those points, or maybe let me. So if I do a point here and run the program, so I want to have a vortex at each of these points. So there were 35, and I want to have a vortex at each of those points. So how do I do that? This is where my vortices are defined. The x coordinates of my vortices can be, so I don't want to delete this. Let me just copy this once more. Let me copy it here and then comment this out. So the x coordinates, let us use the panel x coordinates and panel y points, y coordinates, and the vortex intensities. How about making them ones like x? So they are all 1. Let us see in this way. In this case, let's see the flow velocity field. Okay, now I have 35 vertices at the foil points. How do I know the number? Well, this is my foil points and this is the length of that vector. So where I define my vortices here, I have my vortices at the foil points, 1 for each, so I have 35 points. I have a free flow and my vortices. I also define the free flow once again here with the same vortices. So let me now have a look at the projection vectors and the flow due to the vortices. Okay, I think my free flow velocity is a little small compared to my 35 combination of 35 vortices. So let us do that a little larger to see the free flow. As you see now, it is better. I can see the free flow coming, but it also goes through and then leaves my airfoil. I can introduce counterclockwise vortices as well. Vortex intensities can be random. Okay, so this is a random vector, and it can be how many? As many as the number of vortices. Okay, so this will be a little larger, so I can divide them by 3, for example, to make them a little smaller. So I have clockwise and counterclockwise vortices. And to make them even more visible, I can make this free flow smaller, so I have a better view of the flow. Okay, yes, now the vortices are actually disturbing the incoming flow. I can see that clearly. Okay, now we come to the point where in order to define the flow around an airfoil, the question boils down to finding the intensity of vortices. What kind of intensities should I have to make the airfoil, to make the flow nicely curl around the airfoil? How can I calculate those vortices? I want you to think about this question on your own, and then, but I want to show you that this is actually possible. That if you choose the right vortices, it is possible to make the flow go around the airfoil. Let me show you a solution just to show you that. Now here I have a Python script that I completed some time ago that actually gives you the nice airfoils and the nice flow field around the airfoil. Let me run this and discuss the results with you. Okay. So here is the airfoil that we've been working with. But as you see now, the free flow coming in the x direction nicely curls around the airfoil. It doesn't enter the airfoil here. These are very small, or you can ignore this. Basically, there is no flow inside the airfoil. As you see, it nicely curls around the airfoil and then leaves the airfoil to have a nice smooth flow after the airfoil. These are the magnitudes of the vortices. Remember, we did them random, but of course they shouldn't be random. But if you select them this way, the vortices selected for this airfoil, we select 50 vortices. If you select them in this way, it will create a nice smooth flow around the airfoil. And in the next graph here, this actually shows you the flow velocity. The velocity field, the scalar velocity, is higher on the top of the airfoil and almost zero inside, because there is no flow inside the airfoil, and a less speedy flow. The magnitude of the flow velocity is lower at the lower part of the airfoil. Now, of course, I didn't tell you how you can select the right vortices. That is the main question. I want you to think about how can one find out the right vortices to make the flow go around. My point in showing you this graph is that yes, it is possible. I am actually doing exactly the same thing. For this type of an airfoil, choosing the vortice intensities in this way gives you a nice smooth flow around the airfoil. But how one can calculate these vortices? I would like you to think about this problem, and we discuss it in the uh, class hour when we meet on Microsoft Teams. Okay, thank you.